Okay, we're going to get started with the problems on chapter 14. This is the chapter on heat, looking at conduction, convection, and radiation. And the first few problems are related to heat capacity. The first one of these we will be doing is problem number 3. And problem number 3 is a simple problem that states to sterilize a 50-gram glass baby bottle, we must raise its temperature from 22 degrees to 95 degrees. How much heat would be required? Now, the formula for this is that the heat required is equal to the mass times the specific heat of the baby bottle, the glass, times the change in temperature that we want. In this case, we're going to have now all of the data in the tables is in kilograms, so we need to change this 50-gram bottle into a 0.05 kilogram bottle, and the heat in terms of kilograms is 0.2 kilocalories per kilogram degree centigrade, and then the change in temperature here is 73 degrees. And so if you do the math here, you end up with 0.730 kilocalories of heat, or 730 calories. Now, if you happen to do this in terms of joules, you just multiply this number by 4.19 joules per calorie, and it'll give you the answer in joules. The next problem is problem number 6. Problem number 6 states that a 0.25 kilogram block of pure material is heated from 20 to 65 degrees by the addition of 4.35 kilojoules of energy. Calculate its specific heat and identify the substance of which it is most likely composed. Now they use joules here. Again, the formula is the same. Q is equal to m C delta T. Now we want to know C, and so C is going to equal to Q divided by M delta T, and Q here is given as 4.35 kilojoules. Now in the table, it's actually joules per kilogram, so let's say this is 4,350 joules divided by, and the mass is 0.25 kilograms, and the change in temperature is 45 degrees centigrade. And so if we do the math here, we get 387 joules per kilogram degree centigrade. And if you look in the table, this is copper. So it tells you that the substance is copper. Number 8. Number 8 states the number of kilocalories in food is determined by calorimetry techniques in which the food is burned and the amount of heat transfer is measured. How many kilocalories per gram are there in a 5-gram peanut if the energy of burning it is transferred to a 0.5 kilograms of water held in a 0.1 kilogram aluminum cup, causing a change in temperature or an increase in temperature of 54.9 degrees. So what it says here is that the total heat is going to heat water, MC delta T, plus an aluminum cup, MC delta T. So you're going to have two. This is the water, and this is the cup, the aluminum cup. And so if we put the numbers in here, we have a half a kilogram of water, and it's 1 calorie or kilocalorie per kilogram, the change in temperature being 54.9 degrees, and then you have a 0.1 kilogram aluminum cup, and it is 0.215 kilocalories per kilogram degree centigrade, and the same change in temperature. If we add all of that together, we're going to get 28.63 kilocalories. Now it says how many kilocalories per gram. So if we divide this by 5 grams, we end up with 5.73 kilocalories per gram of peanut. And as it turns out, when you look on the label, the calories they tell you are actually kilocalories. So it's 5.73 kilocalories per gram. Now there are 29 grams in an ounce. So if you multiply this number by 29, you'll find out how many kilocalories it is per ounce. And if we just said 30, you see it's going to be about 170 calories per ounce. Number 9. Number 9 says that following vigorous exercise, the body temperature of an 80 kilogram person is 40 degrees centigrade. At what rate in watts must the person transfer thermal energy to reduce body temperature to 37 degrees in 30 minutes, assuming the body continues to produce energy at a rate of 150 watts, which is 150 joules per second? Okay, so first of all, we have an 80 kilogram person, and we want to decrease their temperature by 3 degrees, and it turns out that you burn it takes 3,500 joules per kilogram degrees centigrade for human beings. So the total here that we're trying to lose is 8.4 times 10 to the 5th joules. Now at the same time, we are burning 150 watts or 150 joules per second, and 30 minutes is 1,800 seconds. That's 30 times 60. And that's going to equal an additional 2.7 times 10 to the 5th joules. So the total here is going to be 1.11 times 10 to the 6th joules that we have to dissipate in a period of 30 minutes. And if we take that 1.11 times 10 to the 6th and divide that by our 1,800 seconds, we end up with 617 watts in terms of dissipation, that amount of energy dissipated. Now the next problem that we're going to do, now we're moving into a new section, and the new section has to do with changes in state. And when you change a state, the important thing to remember is you don't change temperature during the change of state. So for example, in this first problem, problem number 11, it says how much heat transfer in kilocalories is required to thaw 0.45 kilogram package of frozen vegetables at 0 degrees if their heat of fusion is the same as that of water. Now the temperature won't change, but in order to thaw these guys, the heat needed is the mass times the heat of fusion. And the heat of fusion is in the second table in the book, and for water it's 79.8 kilocalories per kilogram. And if we multiply that by the mass, which is 0.450 kilograms, we end up with 35.9 kilocalories necessary to thaw out these vegetables. The second problem, number 12, looks at the same situation. It splices it up between the effect of water versus the effect of ice. And so this is an important understanding. It says a bag containing 0 degrees of ice is much more effective in absorbing energy, absorbing heat, than one containing the same amount of water at 0 degrees. And so to prove that statement, we first calculate how much heat transfer would be necessary to change 0.8 of a kilogram of water from 0 to 30 degrees. So that's going to be Q is equal to MC delta T. So that's going to be equal to 0.8 times 1 from the table times 30 is the change in temperature. So that's going to be 2.4 kilocalories. 8 times 3 is 24, and then get your decimal worked out, and you get 2.4. Now, the second part says how much heat transfer is required to melt and then raise its temperature to this 30 degrees. So you're going to take MHF to melt it, and then you're going to raise the temperature. So it's going to be 0.8 times 79.8 plus what we just calculated, our 2.4 kilocalories. And so if you do the multiplication here, you get 63.8 kilocalories. So melting this ice gives you exactly 20 times more heat capacity absorbed than just heating the water up. And so if you add those two together, you get 66.2 kilocalories. So by just making it ice instead of water, you go from 2.4 to 66.2, which is a pretty dramatic difference, and I think proves the point they're trying to make in the question. The next problem is problem number 17. And problem number 17 is one of my favorite kinds of problems. So it's one that you might want to make sure you understand because it could appear on a quiz or test. It basically asks how much heat is necessary to raise the temperature of a 0.2 kilogram piece of ice from minus 20 degrees to 130 degrees. Now there are 5 steps that you have to include in order to do this. First, you have to heat the ice from minus 30 to 0. And so that's going to be 0.2, that's the mass of the ice, times the specific heat of ice, which is 0.5, times that change in temperature, which is 30 degrees. Then you have to melt the ice, and that's going to be 0.2 times 79.8. Then you have to heat that ice water from 0 to 100 degrees. So that's going to be 0.2 times 1 times 100 for the change in temperature. Then you have to convert the water to steam. So you boil. So that's going to be 0.2 times the heat of vaporization, which is 539 kilocalories per kilogram. And then lastly, you have to heat the steam from 100 to 130, which is 0.2 times 0.363, which is the specific heat of steam, times 30 degrees, which is the change in temperature. So you have 5 steps that you have to go through. This is going to be 2 kilocalories. This is going to be 16 kilocalories. This is going to be 20 kilocalories. This is going to be 108 kilocalories. And then lastly, this is going to be 2.18 kilocalories. And if you add all of that up together, you get a grand total of 148.2 kilocalories to perform this operation. Now the second question says that if you have a constant heater that supplies 20 kilojoules per second, how much does each one of these steps take? Now I did this in terms of kilocalories, okay? And so I could either change every one of these numbers to joules, kilojoules, which would be multiplying each one by 4.19, or I can divide this 20 by 4.19, and I would get it's 4.773 kilocalories per second. Okay, this is kilojoules per second. It's that many kilocalories. So if we divide this number into this, we get 0.42 seconds. If we divide this number into this, we get 3.35 seconds. If we divide the next, we get 4.19 seconds. We divide the next one, we get 22.6 seconds. And then lastly, another 0.4757 seconds. And so the grand total here is 31 seconds to do the whole operation with this amount of power. And then lastly, it asks you to draw a graph of this, and it would look something like this. This first operation, if this is time and this is temperature, this first one takes very little time, and then it's a little bit longer on, this is 3 seconds, so it takes a little bit longer, and then this would take just a little bit longer than this part, and then this would be the longest one, and then lastly this little part at the end. And that would basically be the whole thing. Number 24 states the following. Gram ice cube at minus 30 is placed in 0.4 kilograms of water at 35 degrees. What is the final temperature? In order to do these final temperatures, you have to look at heat loss by the water is equal to the heat gained by the ice. So the heat loss by the water is going to be 0.4 times 1 for the specific heat times the change in temperature. And that's going to be 35 degrees minus whatever the final temperature is. And that's going to equal, first of all, you have to heat the ice up. So that's 0.5 times 0.5 kilocalories per kilogram times 30 degrees to get it to 0 degrees plus 0.05 times 79.8 to melt the ice plus 0.05 times 1 times the change in temperature is going to be the final temperature minus 0, so it's going to just be the final temperature. And then if you do the math here, you're going to get a final temperature of 20.6 degrees centigrade. 20.6 degrees centigrade. Now the remainder is answering some questions which I'm going to go over with you regarding conduction, convection, and radiation. And the first of these questions is question number 9. Question number 18 states, some electric stoves have a flat ceramic surface with heating elements underneath. A pot is placed over the heating element, will be heated while it is safe to touch the surface only a few centimeters away. Why is ceramic with a conductivity that is less than metal but greater than that of a good insulator an ideal choice for the stovetop? Well, because ceramic has an intermediate conduction, it allows the transfer of heat to the pot that's placed right in the immediate vicinity, that is right over top the heating element. But because again it's an intermediate conductor, it is not good enough to conductor to allow the transfer of heat more than a few centimeters away so that you can touch the top a few centimeters from where the elements are. Number 19 states that loose-fitting white clothing covering most of the body is ideal in desert dwellers, both in the hot sun and during cold evenings. Explain how such clothing is advantageous during both day and night. Well, first of all, they select white, and white is selected because it reflects sunlight and decreases the heat from the sun from radiation. It covers most of the body to protect the skin from the sun as well. Loose-fitting clothing traps a layer of air between the body and the clothing, and the air layer acts as an insulator against both heat and coming in as well as heat being lost. The trapped air is an excellent insulator. Trapped air is used in homes with windows because they have window panes that have more than one pane with trapped air in between the panes to prevent the conduction of heat into the house. Also, the use of drapes also traps air and prevents conduction of heat into the house. Number 20. Number 20 states the following. One way to make a fireplace more energy efficient is to have an external air supply for the combustion of its fuel. Another is to have the room air circulate around the outside of the firebox and back into the room. Detail the methods of heat transfer and involved in each. Actually, this uses both. In both of these cases, we're using air as a conducting agent or a medium for convection. When air circulates through the heat box and then into the room, it is acting as a medium for the convection of heat into the room. And this is true for bringing both cool air from the outside as a fuel for the wood, as well as using the internal air. In both cases, we're looking at convection. Number 21. On cold, clear nights, horses will sleep under the cover of large trees. How does this help them keep warm? Well, as it turns out, the night sky is what's called a perfect black body. And a perfect black body absorbs radiant heat. So if you're under the tree, less heat is absorbed and less heat is lost in the surroundings underneath the tree. And so the area is warmer under the tree than out under the stars. When watching a daytime circus in a large dark-colored tent, you sense a significant heat transfer from the tent. Explain why this occurs. Sunlight hits the dark tent and the dark fabric, and the radiant heat is absorbed into the canvas. The heat then radiates from the canvas into the circus area, and you can feel that heat coming off the canvas. Number 24, why are cloudy nights generally warmer than clear ones? You can refer back to question number 22 on this. It's the same idea, the fact that in a clear night, the night sky acts as a perfect black body that absorbs radiant energy. The last question, why are thermometers that are used in weather stations shielded from the sunshine? Well, if you don't shield the thermometer, then the radiant energy from sunlight will raise the temperature above what you really want to measure. When the thermometer is protected from sunlight, then what you are measuring is the room temperature. When the thermometer is not protected, what you are measuring is the room temperature plus the radiant energy from the sun that comes in and strikes the thermometer as well. That ends the homework for this week, and so there won't be any other, there's only